I'm Falcou. I'm an assistant professor from University of Paris South and the CTO of Numscale, which is a company which deals with providing tools for high-performance computing to non-experts in computing. So this talk will be about more like tales about the journey than something else, about the challenge we think people currently faces concerning the use and mastering of parallel programming in general in different contexts, and how we try to solve these problems, and how C++ helped us doing this, and what we ended up with. So parallel programming and parallel architectures is basically the hot topic of since a couple of decades. Most modern hardware's innovation are or were driven by the need expressed by scientific computing community, being, I mean, all the guys doing high energy physics or all the data mining stuff or high-speed imaging. And so parallel architectures is what is the solutions that vendors has found to have this very demanding application be running at the correct path. The problem is that for a long time, parallel architectures was basically something that you will find in very huge company or academia. But now there is a lot of small to medium-sized companies that actually require this kind of performances, either for designing their product faster or to actually be a product in itself, okay? And for some of those companies or some of this research group, it's actually difficult to have the local experts doing the actual science or the actual engineering, and next to that, having people just dedicated to actually know how to program those damn machines. And the problem is actually going, worse and worse as machines become more and more complex. If I just take a look at this laptop I just bought like 6 months ago, it's already a huge beast. I have 4 logical cores with I don't know how many XMD extension set. I have like 3 or 4 types of memory and caches. I have a small inboard GPUs. I have an actual NVIDIA GPU inside with 48 multi-cores inside and his own set of memory. And if I wanted to actually write an application taking care of all of those details, I would have to handle something like 3 or 5 different API and programming models. So if this is complex for somebody which is actually dealing with that as his day-to-day job, imagine how it's complex for somebody which is a physicist or a statistician. And the actual problem is not going to be solved just by waiting for different tools or whatever. For a long time, if we consider the performance versus expressiveness trade-off, for a long time, people didn't have very much choice anyway. So if you climbed up the performance ladder, you will lose expressiveness, but not by much. And doing this, or this was basically the exact same thing, okay? But it changed when we get those multi-core SIMD-enabled processors. Basically, all of this just gets lumped into these sequential blobs. And if you wanted to get to the next level of performances, you get a massive loss in expressiveness, okay? And now it's not even going better. We have GPUs, we have Xeon 5, distributed systems, threading, SIMD, and all combination of that, and everything just get more and more spread out. So the question is, can we actually be around there and around there, okay, which is as expressive as normal languages, and being able to take care of all those kind of performance sources? So that was a challenge we wanted to have a look at. So to do so, because the challenge is not enough, we wanted to have some constraints because it will be too easy, So we wanted to be non-disruptive in the sense that we didn't want to force people to change the way they program all day long and the way they use build systems, okay? It has to be as easy to use as possible. Another point was we found out after a lot of experimentation that the best optimization is not cranking out this very optimized bit flipping algorithms using I don't know what instruction set. It was finding the proper domain-driven optimization that you cannot actually ask a compiler to find for you. You have to have an expert of the domain telling you, yeah, but this stuff, it's really better if you do it this way. And we wanted to find a way to actually incorporate that. The API has to be intuitive. And as the architectural landscape is ever moving, we want it to be easily portable on a wide amount of architectures. And we want it to be efficient. If not, I mean, you can just write Java. So what did we do? We tried to find a way to design tools like C++ library to address point one. C++ because it helped us getting a nice abstraction layer and a nice API, and the libraries because library are trivial to use. We designed those libraries as domain-specific embedded languages, what we get on what these stuff are a bit later, which help us giving this API stuff with this domain optimization layers. And we use a parallel programming model called parallel skeletons as parallel components to help us with the 4 points, and use generative programming to ensure performances. So all this stuff get together. Well, the problem is that if you use unstructured parallelisms, writing a parallel program is very hard, okay? And you will have hard time debugging it, you will have hard time making it portable, and so you don't really want to do that. What you want to do is actually use a model for your programming, your parallel program. So there's a lot of parallel programming models, either based on some kind of parallel performance model, like all the PRAM, logP, and BSP models. Okay, you have data-centric models where the data structure and the semantics will drive the parallelization. That was PGAS and all PGAS-related stuff does, or HTA. And you have what we call pattern-centric models, which are actors and skeletons. So we decided to use skeletons because they have a lot of nice properties. So what's a parallel skeleton? So parallel skeleton was something designed in 1989 by Miracle, which are designed them as patterns in parallel applications, the same way you have patterns in sequential application. And those patterns can be generalized and turned into something you can assemble and compose. And being composable is actually tremendously useful in parallel programming. And from a functional point of view, skeletons are higher order functions, which means that they are functions with parameters can be other functions, okay? And trivially, those function arguments can be your fine-grained sequential operation you want to orchestrate on your machine. And basically, writing a parallel application is just composing skeletons and your function into a stateless object. So basically, there is a couple of classical skeletons that we will just find out trivially. You have map, which is basically applying the same function to everybody into a data set. For that perform reductions, scan, which basically resemble what you can find to the standard library, actually. And you have task-oriented skeletons like par, which is basically I have a task there and a task there, and nobody talk to each other. Okay, so you can just partition your parallel system this way. Pipeline, which just make task dependency over time, and farm or slave masters, depending on where you go, is used for load balancing issues. You basically have a stream of data coming in, a pool of slave processors, and you will just distribute the work to those slave processors as time goes. And actually expressing a parallel application, by using combination of that is trivial, and it just looks like functional programming anyway. And you will just have to find a way to decompose your problem into the skeletons. So I don't know if anybody is familiar with Mapreduce, the Google stuff, right? Who knows about Mapreduce? Okay, so basically Mapreduce is parallel skeletons, okay? Even if they claim otherwise, that's basically, well, map and for, that's Mapreduce. And, well, the thing is that you can actually write your application without having to deal with parallelism details. You just say, I'm composing those skeletons one into the others, and done. It doesn't have to do anything to maintain it, except being sure that the implementation of each skeleton is correct. And some clever math guy actually demonstrated that you can actually reason on skeleton composition and prove that your program is parallelly correct, which can be something nice to have when you work on certified environment. And if the semantic of the each skeleton is set in stone, implementation is free. So you can have a map over a bunch of SIMD vectors. You can have a map distributed over threads. And you can distribute over thread using pthread, using Openmp, using TBB, whatever. You can distribute over network, same stuff, it's map. So we can just use that as some kind of layers to access the hardware and just live with that. And whenever you compose skeleton in itself with different architecture supports, you just emulate support for hierarchical architectures. So if you do a map on MPI that just call a map on Openmp, calling a map on SIMD, you just go down your architecture's hierarchy and everybody is happy and works together. So that's the kind of model we wanted to have to be able to simplify the amount of work we wanted to do. And so the question is, how to have all those function composition of sequential function be efficient at the end. So the model of development we took was what we call generative programming, which is something that was proposed in 2000 something by Snarzewski and other guys, which basically is all we want. So Snarzewski says that every complex application can be derived from a domain-specific description of the application that gets passed to a translator, and this translator will pick up components that can be parameterized depending on what kind of patterns are found into this description and the actual type used into the description. And once it picked up the components, it will just build whatever it needs to be done for the application. And what we found out is that, let's say we want to do this and use our barrier skeleton, whatever. Barrier skeleton will just be there as subcomponent of the systems. And we can just take this domain-specific description we wanted to have anyway, point 2 and 3, get into that and find a way to do this. And the question, how do you write this translator? Well, how many of you went to Walter Brown talk yesterday? Okay, so solution is metaprogramming, which is just metaprogram everything, okay? So, in fact, there is multiple ways to do generative programming. Either you write your own compilers, it works, not very efficient in terms of times and efforts, but it works. You can use external preprocessing tools like P4 or whatever, or you can use metaprogramming. So for the guys that were not into Walter Brown talk yesterday, metaprogramming is writing of computer programs that can analyze, transform, and generate other programs as if they were data. So a program is just a bunch of data you want to manipulate, okay? And, well, how to do that in C++? So C++ metaprogramming just rely on the C++ template sublanguages, in which you can handle types and integral constant at compile time, like it was actually a pure functional languages. And in fact, you can prove that C++ templates in itself is a Turing-complete language. So you can do arbitrary computation at compile time into the C++ compilers. And when I say arbitrary, I say arbitrary. And that's cool because, well, one stuff we wanted to compute is we have a description of languages and we want to turn it into something else. How is it called? What's the name of tools that take a language description, or a program written in some languages, turn it into something else? That's a compiler. And the compiler is a program, so you can write a compiler using some languages. So what about writing a compiler using metaprogramming? Okay, so to do this, well, you can do that, like, you know, using whatever, but let's have a method to our madness, okay? So we go back to this definition of domain-specific embedded languages, DSEL. That's a mouthful. So what's a DSEL? So what's a DSL first? So DSL is domain-specific languages. It's a small, usually declarative language that can be used to define a way to express solution to a very narrow set of problems. If you ever wrote a makefile, you were using a DSL. If you ever wrote SQL, you were using a DSL. Okay. So DSL can or cannot be Turing complete. That's not a problem. And what's a DSEL? Well, it's a DSL that just is embedded into another, usually general purpose languages. So to do this in C++, well, we will just abuse or use, depending on which side of the fence you are sitting on, operator overloading, and using a very well-known idiom, which is expression template. I will get on that afterwards. And using this, we can carry arbitrary semantic information on code fragment. So we can capture a fragment of statement and slap some information on that. And we can just pass around those code fragments as far as we want into the evaluation process. And whenever we need those extra informations, we can just pick them up and do whatever we want. And we can actually turn a code or a library self-aware of a possible optimization. That's what Julian called active libraries, which allow us to do a very simple thing. We will be able to capture arbitrary statement abstract syntax tree as a whole, and note them with high-level semantic information. And we can actually, at the expression level, generate arbitrary code from this IST and those information. Or, which is even better, we can just pass ISTs around as parameters of functions to trigger some form of interprocedural optimization. Okay, but we can do that with whatever semantic we want. So basically, expression templates are just compiler inside the compiler. And to do this, what we do is we use Boost Proto. So we doesn't have to write all the clutch types and machinery. Well, that's something, okay, that could be cool if I didn't copy-paste the same slide twice, whatever. So now we know about that already, okay. So what are the advantages? Well, we can actually introduce a DSL into C++. This DSL can be as specific to the domain as possible, okay, right? And we do this as a library so nobody gets disrupted, okay? And as we define types to carry the semantics, that means that we can resolve semantic-driven optimization at compile time. And as we didn't have any information about what's going on, we can bind to arbitrary runtimes later on. So basically, just like we put a language into your language and we compile, we force the compiler to compile what we want. So an example, let's say, for example, we want to have this kind of matrix-based operator stuff going on. So if we look at this statement, okay, what happened is that if you were a compiler, you will see that as something that resembles this tree. Okay, I'm assigning something to X, and this something is the sum between the cosinus of A and the product between B and A. And this tree there is basically flattened into these very complex types. Okay, that's the type. Okay, that's the declaration, that's the type, which is basically a flattened view of this. So it's an expression of assignment between a matrix and an expression of plus, etc., etc. And the interesting point is that in red there, you have the structure of the code, okay, what's going on the node of the tree. And we have information about what is manipulated by the tree, A, B, X, and so on. Okay, so if we look at that, this types is basically this. So we can apply arbitrary transform at compile time and turn this into something else. And for example, we can say, yeah, well, what about turning that into an actual loop nest, you know, going over every element of every matrices, and we just turn that into an element-wise computation of what's inside the matrices. Okay, so blue for the data, red for whatever is going on in the tree. And let's say you have information there about what kind of architecture you have. Well, what about slapping some Openmp pragma on top of that, or vectorizing this, or doing both, whatever? So this transformation there, we can do whatever we want. Okay, if you wanted to turn this into a string and ship it to a Fortran compiler or to a GPU or something like that, we can just do that. Not a problem. We can do whatever we want. But if to do something meaningful, what we actually need there is static information about the architectures. That's something we have to add. So this code actually do whatever we want on a given architecture. So basically, if we just go back to this definition of generative programming, what we do is that we just add another layer on that. So we add the domain-specific application description there, to which we pair a domain-specific architecture description using a small DSL describing architectures in a hierarchical way. This stuff gets translated into architectural components, which are actually instances of the skeleton we need on a given architecture. And once we selected that, we pour everything of all those skeletons into this, which is the components for the applications that get translated and built from a pre-selection of the proper implementation of each component. So we feed the compiler two information. This is a high-level description of whatever I'm trying to do. Okay, let's figure out how to do it properly. And this is a description of what kind of architecture you have and how you should be able to exploit this information to give me the proper component to generating my efficient code for my application. And the point is that everything from there to there is basically happening at compile time. So we will probably have zero overhead at the end. That's what we want to be at the end of all of that. So what do you do with all of this? So what we wanted to have is some kind of demonstration that we can actually do this in a lot of different scenarios. Demonstrate that parallel skeleton is a viable parallel programming model for that, and that with a sufficiently advanced metaprogram systems, we can actually go from point A to point B without having to go outside the C++ compiler. So we did a bunch of stuff. I won't talk about all of that. So we have BSP++, which is a generic C++ BSP library. So BSP is a very constrained programming model, which has a good idea to have an analytical performance model. So whenever you look at your algorithm, you know by advance how many times it will take, okay? And that both work on shared and distributed memory. We have QAF, which is a DSL for direct skeleton programming, not very interesting, just there for historical purpose. We have Boost SIMD, which is a DSL for an actual portable SIMD programming style that also happens to use skeletons. And we have NT2, which is a MATLAB-like DSL for scientific computing, which we'll speak a bit more about right now. So what's NT2? So NT2 is a numerical template toolbox. It's basically MATLAB in C++ without all the craft and with actual performance. No, okay. And which is designed to actually be working on whatever CPU or GPU you have and be easily extendable. So it's built onto two layers. So we use Boost SIMD and all the related tools for the in-core optimizations, and we use recursive parallel skeletons to build up on multi-cores and other systems. And your code actually is independent of the architecture you want to target and the runtime you want to use to exploit these targets. It means that if you are on multi-core systems and you don't really know if for this very particular application, Openmp could be better than TBB or pthreads, well, you can just write your code once and compile it twice with different options on the compiler to choose between those three runtime, and you can compare performance quite fast. So this is a bunch of feature lists. So I know that this table looks like a Samsung versus Apple comparisons, okay, but we did our best. So we have a MATLAB-like API. We have bindings for BLAS and LAPACK runtime because linear algebra is a job in itself. So and currently that's the best stuff out there. We have one of the few Magma bindings. So Magma is the GPU version of LAPACK. So whenever you use NT2 on the GPU systems and you use linear algebra, we go on the GPU in a transparent way. Okay. We basically support whatever SIMD extension Intel ever thought about, including Xeon Phi. We have support for PowerPC and for ARM, multi-threading, and we have a prototype for CUDA supports. So we basically run everywhere. We try to have decent to very decent performance everywhere too. And so, okay. So what does it look like? So this is a simple principle of what you want to do when you write code with NT2. So you have a very simple multi-dimensional array, which is called table, that just happens to work like MATLAB array. So it has a variable number of dimension between 1 and 4 or 5, I don't remember right now, and whatever function you want to use it. So the joke we have is that, well, if you want to do something, just look up the MATLAB documentation and just write the damn function into your C++ code, and it will probably work 90% of the time. So we have over 500 functions of maths, signal processing, statistics, whatever. And just work on table, on scalar, in a transparent way. So how does it work? So let's say you worked with MATLAB first. It happens, okay? So you take your MATLAB code, you copy it into a C++ file, you add some includes, and you do a bunch of changes for syntax reasons. You compile, and well, that's done. You finished. You converted your ugly-like Matlab code, which were probably slow, into a C++ version. Okay, that's what they say on the tin. Okay, so let's have an example. So, how many of you are actually familiar with Matlab syntax? Okay, so we'll explain that. So, first line, what we do is we create an array called A1, which basically contains number from 1 to 1,000, spaced regularly. And then we decide to add a normal distribution of random numbers to A1. And what we do is that, well, we compute some matrix product between A1 and its transpose, and we do a LU decomposition into X. And for whatever reason, we compute the square root of the sum between A1 squared and A2 squared, divided by the number of elements in A1. Okay. Well, how do you turn that into C++? Well, you just do that. So contrary to Matlab, we need types. Okay, so let's say table of double. Colon is not a valid symbol that you can put anywhere in C++, so we turn that into underscore. Okay, random is random, and size is size. Numeral is numeral. Okay, and LU is LU. So the tick for the transpose become a transpose function. We have m times for the matrix multiplication. Everything is basically the same, and we found also this colon there. So what does it mean? Colon in an indexing context in MATLAB means every element along this dimension. Okay, and when you use it like this with only one dimension, it means every element, in these matrices, okay, but in a column-wise fashion, okay. So we can, the same way we turn this column into this underscore, we just reuse underscore in these places. And done. That's all you have to change. This, a bunch of other functions like that, okay, and that's pretty much it, okay. So it's designed to transform this Matlab code into regular C++ code quite fast. Of course, you can actually write directly C++ code in it. And for people that really want to be working with C++, we are obviously compatible with the traditional STL concept. So a table is a random access sequence that gives you iterators and so on and so on. So you can actually go back and forth between C++ style and MATLAB style code using this. So that's not a very interesting code, but just to display what we can do with that. So, but how does it work? Okay, in practice. So I have this, because I spoke about skeleton and so on. So how does it work? So let's say you have this statement. A equal B divided by the sum of C plus D. Okay. So basically what you have is that you have this AST. Okay. And what we do is that at compile time, every node into this AST is flagged with something that tells us what kind of loop nest this operation will prefer. And if you look at that, you see that you have an element-wise operation going on there. We will divide B by something, okay? But this something is a partial reduction, okay? So it needs a different kind of loop nest. So what we really want to be able to do is extract this subtree, evaluate it into a temporary, and put the temporary back so we can have a properly, orchestrated loop nest. And that's what we do at compile time by just scrolling down the IST. We will just slice the tree, okay, put that into a temporary that gets referenced there, generate the first loop nest using the fold skeleton, and then use the transform or map skeleton to perform the rest of the operation. And if you look at that, you see that we sliced there because we were combining element-wise operation with a reduction, but in the case of the reduction, we can actually keep the element-wise operation inside because reduction of map is composable where map of reduction is not. So we are able to detect this kind of patterns and slice it as we wish. But there is a problem. What happens if you do that, and let's say you want to generate code for this, so every loop nest is trivial to generate, and let's say you do that using an Openmp backend or an Intel TBV backend. Well, you will have a first parallel region over there, okay, and then another one, and they will get separated by a barrier. So we could be very, artistic and tricky and try to use Openmp no weight because we are, we like gambling, and so let's pretend that I cannot wait there and everything will work correctly. Normally what will happen is that it will pass the test, but every time you will deploy that on the client, it won't work. Okay, that's how lights work. So we really want to have a barrier there. But if we start having a barrier every time we change, loop nest, it will be costly, and it's even worse without having Openmp actually. Let's say you have multiple statements. The power of expression templates only stops at the first semicolon you find, okay? And whenever you have another statement going on, it's another context, and the expression template system doesn't know what was going on in the statement before, and you will generate loop nest over loop nest. And if the algorithm is meant to not to be a bit more optimized than that, and you will basically trash your cache locality because you will keep going over and over again in different loop nests, and you will get bad performances. So you get bad performances because either you have barriers between statements or because you have a poor data locality. And we wanted to find a way to fight against that. First idea was, well, let's turn a semicolon into something that the expression template system can recognize. So what about abusing this poor comma operator so you can change statement with comma, all over again and all over again. And so you will get your expression template growing up until the first actual semicolon. Well, the bad news is it works. But if you ever want to see a C++ symbol which name makes 1 megabyte of characters, that's what you want to do, okay? So when we were compiling this kind of stuff with debugging symbol inside, I can tell you we can actually compile the code, at 11:30 something, go to lunch at home, cook something, take a, very comfy lunch and come back, get a coffee, and we probably not finished compiling yet, okay? Around at 2 or something. So it was not very practical. And the other issue is that this tricks was using destructors to trigger the evaluation of the statement. Because basically what happens is that this comma sequence builds the temporary objects containing all the expressions. And the only way to force the evaluation is to wait for this temporary object to be destroyed. And we should evaluate everything. Well, except what happens if you are on a distributed systems and you want to catch an exception because some of your nodes just dropped and the system of transferring the data just raised an exception. So you get an exception raised in the destructors, which probably means you never catch it. Okay, so we ditched that. Because, well, issues and reasons. And, well, we turn into something else which makes more sense. I will show you one solution there for the shared memory systems, and we'll show another one into the example for the regular system. So on a multi-core machine, let's say, what we really want to do is enabling some kind of task pipelining between statements. That's what we want to do. Okay, and instead of doing like stupid guys, okay, let's do it properly. So we added some more skeletons to actually express this notion of pipelining, okay? And we use futures, so either from standards or from HPX, to automatically create asynchronous pipelines between statements. And what we do is that we take our IST, okay, so the IST goes this way, and if you take your tree and you put it on Z, and you go from up to down, what you have is your dependency graph between tasks, done. So what happens? Well, remember that what we really want to do is putting TMP into a future, fire that into some bunch of threads, and then start that and wait for TMP there, put into a thread, and probably go see what the next statement is all about. Because I don't have to wait for this to be completed to go to the next line. So I just asynchronously go over all my expression template statement and fires futures for each part of them automatically, directly from the expression template layers. So this basically gets turned into that, okay? So we slice every loop nest over different bunch of data blocks, so we can have multiple grain-sized block over there, and every stuff there just fills these futures that get pipeline over there with, in this case, the same number of workers. And what happens? So we go there, extract this, feed it into a futures-like object that we just generate all those workers working on subparts of the expressions. And we forget about that, and we go to the next one that just builds the same kind of working elements waiting on these futures. And then we go to the next statement if there is any other statement, and so on and so on. And magically, every futures will complete some point, trigger whatever is next, and you will just crumble down all your IST tree without having to know the sequence of them at compile time. And actually, it took us a long time to go there because we were quite certain that doing all of this at runtime will eat up all our speedups. Because, you know, allocating a bunch of workers in the vector, firing, you know, futures and so on. And actually, well, it was actually faster than the ugly, you know, comatrix. So we forgot about the comatrix and did that. And it scaled actually very well because as long as you have, I mean, if you have a very long single element-wise expression, not a problem. You get a very nice deep tree that you will generate multiple workers for it and just wait for that, okay, and go to the next stuff. You'll probably be non-related to this guy, so you will fire another bunch of futures and so on and so on. And if you happen to find out something like A equals B plus C, Z equals 1 over A, so all the expression template system will just do the your A equals and block, okay, and you will do the your Z equal, rereading every part of A and block. In this case, well, you slice the stuff computing A, fire futures, go to the next stuff, and just wait, and so on and so on and so on. So it just works, actually. That was the funny thing. So some examples, okay? I've selected 3 very simple demo for different purposes. This one is actually something we like very much because the algorithm is actually something that makes sense, and it has a lot of changes. So this is a motion detection algorithm using an algorithm called sigma delta, which was proposed by LAPACK and I forgot the other name. And the idea is that when you do motion detection, usually in imaging, what you do is something rather naive, which says, okay, I have my frame coming at T1 and my next frame, and I just do a pixel-wise, you know, subtractions, and I will just apply some threshold, and whatever is above the threshold is moving. But if you have an image where the contrast is very different in different parts of the images, you will have an hard time finding a proper threshold that will get what you want, okay? So the sigma delta algorithm is very smart because it basically has a Gaussian model of the lightness on every pixel. And whenever a pixel change its lightning value for more than 3 times the sigma of the distribution, that's movement, okay? So basically you have tons of small Gaussians going on every pixel. It looks complicated and slow. And actually, when you look at the algorithm, you can implement it with like addition, subtraction, and test. That's very impressive. And it works with very, very few operations. It has a very low arithmetic density and is basically bound up by memory access. And it usually uses small integers for its implementation. And so the challenge was, how far can we go compared to the actual state-of-the-art implementation of this algorithm written by hand in C? So the entry to code is actually rather small. So what do you get as an input is the background frame in which we will put all the pixels that doesn't move, the actual new frame you want to process, and the table containing the variance, okay, of the pixels. And what you do is basically comparing the frame to the background and updating the background accordingly by either decrementing it or incrementing it conditionally. You will compute the distance between the background and the update and the frames. You will compute the value of the local variances, and depending if there is any difference, okay, well, either you update the variance or you let it go like it is. And where are the movements? The movements are everywhere the difference image is bigger than the variance. Done. So how many operations is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, well, 12 operations, something like that, working on chart. That's a very nice algorithm. Okay, everything is completely parallel everywhere. So it's trivial to implement a SIMD version of these algorithms. That's what's done into the reference paper we used. Okay, so that's what we got as performance. So we compute the number of CPU cycles we consume to compute 1 pixel of the output. Okay. So the scalar version written in C. Okay. With the latest version of GCC with all the auto-vectorizing option on, okay, to have a fair comparison, give us something around 16 or 18 cycles per point, okay, for 512 squared images. And basically the same speed for the 1000 by 1000. So let's have a look at what is this color? The blue color, yeah, small light blue colors there. So this is the actual reference performance from the original paper, okay, written in C and whatever, okay, using SSE2. So you basically go from 116 to 1.5, 1.6. That's a 10 times speed up, okay. And so what do we do? So we can actually use just a SIMD, okay. So you take your NT2 code you saw there and you compile using -m SSE2, just that, and we got to a bit above 2, okay? So we have a speed up of 7 instead of 10. That's not bad. Or we can use multi-cores using Openmp. So this is a 4-core machine, yeah. So with 2 and 4 cores, okay, and we got pretty much what we expect to get, okay? And we can combine SIMD plus Openmp. So GCC myfunction.cpp -m SSE2 -f Openmp, done. And we get a bit more speed up, so 15, 16 and a half, 15, 18, okay, which is actually not 3.6 times 6.8 because around there at about 1.8 cycle per element, we just hit the memory barriers, okay. That's the time we spend just loading the values and there's no way to go faster than that. Well, probably a bit much, but not much less than 1 cycle per element. So if we look at this side, we have decent performance compared to the actual references. Okay, so 10 to 7. That's with basically no efforts. And when we combine with Openmp, we just continue. I don't have the slides there. I don't know where they are, but we just implemented the same algorithm using AVX2, which is supporting 32 wide register of unsigned cars, and we get a speed up of around 27. And we didn't even touch the code. So we can actually go pretty far into, being close to what, an expert could have written by hand, using whatever tricks he knew about. So he doesn't have to use the tricks. We know them and the library use them for you. So another example, which is completely different. So the classical, let's compute the Black-Scholes call and put price, okay, using the classical implementation using NOM-CDF. So I'm completely not an expert into this algorithm. So tables goes in and the value goes out, okay, but don't ask me what's going on, okay. The only stuff I know is that it's very easy because you have log and exponential and NOM-CDF, which is basically a polynomial approximation of the norm of the error functions. Okay, this probably eats up like 100 cycles per point alone. Okay, so that's the way to do it. So you have some intermediate tables because we want to not be computing stuff too much. Okay, and you just apply the function, right? And you look at the result of that. And we will see later that, well, it goes faster, but it's not very spectacular. Why? Well, we have 1, 2, 3, 4 statements. Okay, and every time, as I say, we do a loop nest and another loop nest and another loop nest. So if you compile this code using shared memory systems, the future systems will kick in and just do the right things. So now let's pretend you cannot run this on a multi-core system for whatever reasons. Well, you can manually actually apply loop fusions operation. It's a quite simple way to do that. So you will actually pre-allocate all the temporaries there, and you will use a tie function that basically say, okay guys, I have all those 4 tables to fill in, And this is the fourth statement I want you to put inside. This one into this one there, this one there, and this one there. And this generates a single fat loop nest in which we will just evaluate every statement one after the other on the same point, basically getting back the data locality and the performances. So that's another way to solve this multi-statement problem. Sometimes you want to use it even if you have futures, because for whatever reasons of the algorithms, the futurization makes the cache unhappy for whatever reasons, and you want to do that. So we just let that for the users. So the funny thing is that, yeah, it looks like Thai from the tuple library, but no tuple are actually created, okay? This build an expression object that has a special assignment operators. I will just say, oh, if you give me a Thai there, I will just take that and, you know, do the zipping of everybody. Okay, so nothing actually leaks out of that. So this is the speed up you get when you do that stupidly, okay? So the Scala versions, again, C, optimized, blah, blah, blah. It's 150, a bit less than 150. The SSE2 version is rather bleak, okay, 1.89. AVX is not better with 2.9, okay. And for the, for the exercise, we just disabled the futurization using Openmp there, and we got some speed up, okay. Not much. And now we put everything back and we use Thai, we go basically twice faster. Okay. Well, a bit less than twice faster for there, but we basically hit the limit there, and we go up to 12 times faster when you use AVX2 and the Falcou machine. So we can actually have this kind of control on the code you generate. Okay, we are working to have more options, like you can actually specify that this very statement has to be unrolled this much time if some conditions are met, and so on and so on. So you can basically write your code naively first. Okay, just write the algorithm. You look at the performances, and either everything works out of the box, done. And if not, you can actually have a look at why it's actually not delivering performances. And we have all those small tools, let's say for advanced users, so you can actually take back the control on the generated code. Okay. But if you doesn't know what to do, well, it's not a problem. If you just want to have something that runs relatively fast, just write it and it's done. And another case where this futurization system is very cool is that we can actually take complex algorithms like LU, for example, and turn it into a full-blown asynchronous algorithm. So there is actually a way to write LU decomposition in an asynchronous way, because if you look at how the LU decomposition works, so you will solve a small system on the corner of the matrices. You will update the panel below and the panel on the right, and then go to the next diagonal block. But the next diagonal block doesn't care if the panel are done yet. So you can actually you have your critical path along the diagonal, and every other panels, you don't give a crap, so just put it into a future. Okay, that's what this non-trivial diagram tries to tell you. Okay, so you have basically 4 kernels, so a triangular factorization, I don't know what is that. Another kernel doing another stuff on some panels, another factorization for the other panel, and so on. And you just go down this tree for every block in your matrices. And what does it give you? So that's the work we do with Artmode. Okay, so this is a 8,000 by 8,000 matrices, dense, and we apply this LU decomposition on it. Between 1 and 48 cores. I think that was Hermione, no? So I don't know. Yeah, so that's what. I don't remember.
That would have been an AMD.
Oh, that's an AMD machine. Okay, sorry for that. And so actually the red stuff is Intel MKL run on this. So I probably suppose that it's not that great because it's an AMD machine. Knowing Intel, I hope there is no Intel guy in the room. No, it's okay. So Intel MKL on this machine caps up around the 95, 98 gigaflops, and we just climb down up to 135, okay. And the code to call that is just x equal lu of y. Done.
Just looking from the graph, my guess is that that's completely valid, even though it's
I don't know. Well,
because it's clearly in an image too.
okay, so this guy told me it's actually valid. So I'm always wary about benchmark using Intel tools on non-Intel processors. That's why. But well, anyway, even if we stop there before these crooky behaviors, we are basically in the same ballpark than MKM. Okay. And that's something we just do now on a lot of different LAPACK style algorithms. We just turn them into some kind of futurized algorithms. Okay, and well, just walk out of the box. So, okay, so we did all of that. We got these tools. The question is, what did we learn of all of that? Okay. What a timing. First, some philosophical stance. Okay. We think that building software libraries as a generative systems that just rebuild itself is exactly what you want when you deal with parallelisms for various reasons. Because the hardware changed so much, and you want to be able to regenerate whatever variant of your code, and because at the user level, you may have different need at different time, and you want to have some kind of adaptive tools for doing this. The other stuff we learned is that it's a very well-known stuff that when you write a language in a compiler, if it doesn't have any architectural information, your generated code will just suck. Fact is, for DSCLs, that's the same point. If you don't give your expression template or whatever DSL generator codes some information about the target architectures, well, you will get bland code and bland performances. The question was how to actually inject all those knowledge into the systems. And by integrating this description into the generic and generative process, just actually increase the tool portability and performances. But it's not, for me, it's not enough. We need to formalize those generic and generative components with respect to parallelism and with respect to the languages. And what I really want to do is turn all those big quote acts like expression templates, programming generative programming using policies and tag dispatching and whatever into some kind of actual language features. Because I think as users of C++, I should not have to write all those crooky, damn complex voodoo C++ template magic to get that. It should be like out of the box with using some kind of tools provided by the languages. So currently what we try to do is looking at concept first. The first idea is that instead of having a tag-based system for saying, oh, guys, this function, it's totally a reduction, just let's slice it. Just use concept overloading, okay? Get your IST and have your IST model some kind of concept depending on what kind of parallel operation is being done, and just use C++ concept overloading to slice the operation, okay? So you need stuff like, is this stuff a data parallel IST? Is this operation associative? Is this something I can turn into a reduction and so on and so on? And see how C++1y concept can help us do that. That's something I want to try. Well, that means that we could actually have a public interface for advanced users to write new skeletons into the systems. Because instead of having to tell them, oh yeah, you have to add these 12 different types and these 12 dispatching stuff and probably this 100 stuff so the system can actually know what you want to do, well, just model this concept and it will be done. Okay. And concept refinement could actually help us extend the stuff by, for example, having, okay, I have a data parallel map-like operation that can be refined in a enrollable data parallel operation and so on and so on. And we can actually use static asserts on function properties so you can actually have, well, decent template error messages, okay, which is the main issues with this kind of techniques. If you are into gigabyte-sized, log of errors from GCC, well, don't change anything, okay. But I heard, and some of our clients say to us that, well, it could be good if you could actually have meaningful message that doesn't, fill the screen for 5 minutes, okay? So, well, could be great if, okay, I can actually have some kind of lazy evaluation system directly into the languages, okay? And so I can directly interact with the with the IST representation of some statement and do stuff with it. Okay, and we also think that SIMD operation. We are in 2014. Okay, SIMD is out since what 1993 something. That's how many times? 20 years now. Could be damn cool if it will be like in the standard too, because like, well, everybody uses it. Okay, well, everybody should be using it. So, well, we're working on that actually. Could we have some kind of IST of operation that just give it a statement, give you some kind of standardized expression tree, and you work with that and done, okay, instead of having true oops. So I computed that when you use stuff like Boost Proto or an handmade expression template systems, the compiler actually compiles the IST of one statement 5 times. Okay, the first time, because you have to know what's going on, and then it has to regenerate the type inside the expression template type systems, and then it has to pass that again to know what's going on into each part, and then again when it generates the code. That's a bit much. Okay, so can we have some kind of either IST of operator or meta types keywords that you can say, oh, f of meta t, I don't want a value, I want the IST of whatever you pass to me, and I will deal with it inside, something like this. The main issue is that it will probably requires vendors to agree on an intermediate representation of the IST, which may be problematic, especially on some compilers which I won't name, that doesn't even have IST in the first place. Yep, I will let you guess which one. Another problem with expression templates is, okay, fine. I can write A equal B plus C and something magic happens, okay? And I'm working with C++11, so what about writing auto A equal B plus C? Question, what's the type of A if B and C is captured by an expression template system? Well, it would be some kind of ugly ass type, okay? And probably not a matrix or a string or whatever types you want it to be. So what you may want is have a way to say, yeah, you know, this auto operation there, in fact, that's not what I want. I want the whatever underlying types of my expression. So we wrote a proposal for that with Peter Goschling and Upsutter. I'm not sure the number is right, probably this one. Yes, about having a customization point for operator auto. So you can say, oh, I have a type, and when you do auto on this type, actually, it's this other type. Okay. It looks quite ad hoc for these issues, but actually also simplifies the handling of all kind of proxy types. You have a wrapper or something, okay, and whenever you compute a wrapper or something, and you really want to put it into a something, and you want it to do that using auto, it will become complicated. So you can have wrapper types, changes using auto equal whatever, and get whatever type you want. We also try to get SIMD computation into the standards. That's pretty much botched for different reasons. I'm quoting the end document just for historical, references. We probably try to get that back again, but well, it meets some kind of resistance for whatever reasons. But yeah, so we try to actually put stuff, back into the languages, so we can actually write all of that without having to spend, too much time pulling out our hair from our head and debugging megabytes of error messages. So I think that's pretty much done. So just some stuff we're working on the tool level. So we have this prototype for single source GPU support. So you basically write your code using NT2 in the CPP file. You compile with the proper option to say, yeah, I want that to be on the GPU, and we will derive the correct CUDA or OpenCL kernel directly from the IST inside the C++ code. So it doesn't even have to write CUDA code. We have a PhD student, or two, I don't remember, one, that work on distributed systems, so we can actually support large clusters. Funnily enough, it's quite similar to supporting GPU, because actually GPU is just a distributed system which is very close to your PC, but it's something else with its own memory, units. And we start to have application to big data or data science in general, and try to get meaningful algorithm for this type of application. And what we want to do at the language level, so in addition to whatever I just talked about, is actually have a way to formalize metaprogramming. So it stops looking like a bunch of ugly acts. Okay. Another funky stuff, which is more theoretical, is sometimes you have a DSL for a very specific domain, and people actually demonstrate and certify this language to be correct. Okay. Question is the correctness of a bunch of programs written in a given DSL transferred to the implementation using C++ and expression templates? Do we conserve whatever properties the original language has? That could be cool because you could actually have a certified language for whatever, I don't know, aeronautics or whatever, and you turn it into a very efficient implementation using C++, and you can still say to your boss, yes, it's certified, because this is the proof. And how many of you know about polyhedral model? I should have known that. The polyhedral model is a very interesting model for modeling a loop nest. So the gist is that if you have a loop nest and you look at the boundaries, okay, and you have a multiple dimension loop nest, you look at all the boundaries, and you basically draw a polyhedron into some multi-dimensional space, okay? And the cool polyhedron in this model are the ones that just looks like a big cube or rectangle, because you can just slice it, okay, and the way you slice it is the way you will make it parallel, okay? But sometimes your memory access pattern is more complex and your polyhedron is just some odd shape. And the game is to say, okay, let's take this strange geometry, turn it into a rectangle, and slice it and regenerate code. So this is very interesting because you can actually formalize a lot of code transformation like loop unrolling, loop peeling, parallelization into this model. And it's an actual mathematical model of your loop nest. So the idea is that can we actually metaprogram this kind of stuff directly? So we just look at the expression, build the polyhedron, apply whatever transformation on it before generating the code, instead to have tons of ad hoc optimizer for unrolling and for loop splitting and whatever. So I think that's all. We actually are available on GitHub if you want to play with it and if you have a couple dozen minutes to compile some example. If you actually use that, feel free to send us bug report and whatever. Nope. No, it's still Metascale for whatever reason. It's apparently completely non-trivial to change an organization name on GitHub, so don't ask me, okay? Yeah, so everything is there. We have some issues trackers. Don't hesitate to ping us if you have any issues. If you have exotic systems, we are pretty much also happy to have return of experiment on this. And we're pretty much happy to have any kind of return on this kind of tools and try to make it better for whoever's. So thank you and thanks for your attention. If there is any question.
Okay, I have a question.
You have a question?
I do. So what are you envisioning for changes in metaprogramming things that would make you happy and that would be something that would even be viable for the language?
Yeah, I see. Should I repeat or is it okay? It's okay? Okay. So what could make me happy in terms of metaprogramming? Well, two things. First thing is that the separation between the compile time and the runtime world is a bit awkward due to the template syntax. Okay. One stuff which is very interesting is the way D solved a bunch of this problem. Because actually we use template for doing two things in C++, where we should have two different mechanisms. So we use it for generic function and class definition, okay? And we use it for doing type introspection, basically. In these, that's two different stuff. So you have generics and you have mixin. And what we probably need is whenever I do generative programming, I'm just building a bunch of mixin and mixing them, okay? Well, so the first thing should be split that. I have the template legacy syntax be the generic, way of specifying things, and have something that say, hey, this is a code fragment I want you to carry around and apply whenever I fit it, which is the case, for example, in Meta or Camel or template Haskell. you have a notion, you have a type code fragment of something, and you can just build those code fragments from regular expression, and you just carry it around, and you have an operator for saying, okay, I want to concatenate two code fragments, or I want to evaluate the code fragment into actual code. So that could be a nice thing. And the second thing is that, again, on this compile time runtime frontier, sometimes you just want to have, you have some constant lying around in the runtime world, and you will be very happy if you could actually propagate it into the compile time world. Because I don't see why when I write code which is f of 1, literally, I have no way to know that statically it's a 1. I should be able to do that because it's regularly statically a 1. I want to know it into the other side and know statically it's a 1 and apply whatever stuff I need to that. That's more complex. But already by splitting the way that we use the same frigging syntax for generic functions and code generation introspections could clear up a lot of things. That means that we could have stuff like D actually has a static if and a static for construct that you can actually contract into add something. So you can write add if something blah blah blah, and if everything is constant into the if, well, you basically wrote something like std conditional blah blah blah, except you wrote an if. So the semantic is more clear. It's the same set of keywords, the same set of controls, except the add just turned it into a static stuff. So I don't have to write a pure functional recursive bunch of code to do my loop unrolling. I just write add for something, a bunch of code, and the code gets unrolled. But you cannot do that if you have to be compatible with the old way templates works. We have to split that. You have templates for genericity, and you have this code fragment notion. And that's, I think, the biggest stuff we need to slice around. And the third point, after the two first, is my wish is that the reflection working group actually start to look at arbitrary code fragment instead of values and types. So I can actually ask, introspection about, okay, I have this expression lying around, how many terminals is inside, or how many times do I cross a plus operator in this statement? Because actually, if you have introspection on types and on values, the next step is that you have introspection on arbitrary statement. And I don't think there is much obstacles in writing this into a compiler. It's not trivial, but everything is there already. So you can actually just ask that in a proper syntax and couple that with the fact you split template in two, and you probably have something which is same. For historical reports, the first version of that was written in template Haskell, and it was probably like half or a third of the size for the same amount of ability of building blocks and whatever. So the main obstacle is actually having enough people championing this idea that it's actually useful and not some kind of voodoo style act some guy somewhere actually use for whatever reasons instead of doing normal C++. And that's probably the main issues to get this through. Yes?
Are you familiar at all with the Julia language?
Yes.
Okay.
Yeah.
Because it sounds
that was
like
an easy question.
a lot of your, just a lot of your ideas of how to improve C++ sound like Julia, which
yeah.
Yeah.
The main problem I have with Julia is that when you go to a client, you say, oh yeah, you can do that in Julia. The guy like, in what? So the day it's actually have, it's like D. I wish I can do that in D and still selling stuff to clients. So the day D or Julia or whatever next level languages actually get foot into the industries and people start using it into industrial context, I will take that and just flush it down the drain, okay, and rewrite it into a proper languages. That's for practical reason we're still doing that with C++. But at some point we have to go to people that, already changing from C to C++ was almost a traumatism. So if you want them to go elsewhere, you know it won't fly. So Bryce, you had a question?
Yeah, I was just going to point out that don't people have a point that it is voodoo to some degree?
So
necessary voodoo.
So the question is, people saying that's voodoo, are they right? Oh yes, I think they are right. But the problem is that it shouldn't be that much hassle to do that. For me, the use case of this and the result you can get with that are meaningful enough to say, okay, guys, we should make something so all of this crap could be written like in a less crappy way without having, requiring you to be some kind of, I don't know, aliens from the planet Zogler or whatever. So, but again, that goes with the first point. We need to have traction to make people from the committee or every people around understand that that is not just some kind of playground stuff, and you can actually make, meaningful result with that.
So, I mean, to me, one of the arguments to make, if you look at a language like Fortran, which I would argue in terms of high-performance languages for doing numerical stuff, who's the competitor? Fortran. Who has all these cool features which let you do this sort of, like, built into the language, this support for doing this stuff with arrays? Fortran. And sure, we could add that stuff to C++, sort of the language level craziness for arrays, or we could add the tools to be able to build proper DSLs. Because and then we would have everything.
The thing is that applying that to array-based computation is just the most trivial example you can do.
Right.
I mean, you take that, and I don't know,
converting that to Fortran is,
that's
pretty easy.
That's Fortran.
Yeah.
And one of the reasons that Fortran code is actually faster is not because it's Fortran, because at the end of the day, it's a compiler generating assembly languages. It's because the first rule of Fortran is you have no frigging alias between arrays of different name, periods. And so you can be aggressive on the optimization. And that's basically what we emulate there.
Right.
We force the compiler to know about, okay, it's an array. No, seriously, let me do what I know to do because that's probably best to what we try to be doing.
So I think the argument is to be made is it really does. And yes, maybe it's voodoo, but C++ is a multi-paradigm programming language, and it will enable more paradigms.
What I fear will be the answer is that, but that's implementation QoI details, so we don't give a crap. Yeah. Just use Valerie.
I got a question about the whole SIMD and the standard thing. Is an objection to that for maybe there's embedded systems where you don't have SIMD, and what do you do if
the objection that was nobody give a crap about getting a speed up of 4 when you can have a speed up of 100 using GPU, so you should be focusing your effort on GPU. Yeah, End of quote.
Well, that's silly, but
yeah.
But what?
Oh yeah, and the other funny I have another one. The other funny one was. Why standardizing these kind of technologies that change all the time and are not mature? Yeah. Because GPU is so much mature,
Well, with regards to the mature, it's older than me, so.
It changes all the time in the sense that every time you have a new family of processors, you get new functions, but it's still the same frigging programming model since the 90s.
Right.
So, and GPU SMT is just SIMD in disguise with a crooky hardware to make it work. So,
but if you put it in the standard, what about compilers? What is the solution for a compiler on a platform where you don't have SIMD? If it's part of this,
it's still a linear operation.
Yeah.
Right.
You're doing the same thing to a bunch of data.
What we do is that if you have no SIMD support, we fall back to having a strongly unrolled operation of blocks, on blocks of whatever size you decide, in a scalar way, and you just plop, 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 plop. So having no SIMD is basically the same as having a SIMD instruction set with vector of size 1. Done. End of story.
Okay.
And it's totally, that's not where the problem lies. Fact is that some people think that it's actually a compiler works to do this because it's very low level. But that means that the quality of the auto-vectorization is bound to the compiler you use. In this case, we just do every same damn thing every time. So, But yeah, apparently having C++, automatically going on GPU with a magical keyword on std transform was apparently what people wanted. So, Another question?
First of all, congratulate you for seems to be very good work. We have been working on this type of thing ourselves for many years. Wrote finite element solver with Proto. And needed 4 GB to compile.
All my condolences for that.
Well, it's a very simple question. What's your success on having scientists using this type of thing?
We have a bunch of
Like,
guys.
like scientists that know Fortran, right?
Oh. Well, currently it's very local. So we have a bunch of guys from the our math laboratory starting using that. We have a couple of projects planned, but it didn't fly for different reasons. I mean, government-funded project with some team of the Atlas Sun experiment. We have a bunch of users doing how to say that, instrument simulation. So you can actually say, I want a guitar this way, and I want an effect this way on the guitar, and play that. And so writing DSP code, generating all of this. And we have a bunch of clients doing finance with that.
So mostly expert, kind of expert.
But it's kind of expert into more, I mean, except for the DSP guys, they are mostly non-expert into this kind of thing. Okay. They just wrote the code and it worked and done. Didn't get, lower than that. The DSP guy is a very specific, cases, because usually they know what they want to do, and apparently they found the code generation good enough to don't have to bother going, further than that. So, yeah, but I think we are guilty to not being, more vocal about that and, having a full-blown PR campaign. But well, the project started maybe to be serious like 2 years ago now. Before it was a long, mess of different projects and academical stuff. It gets structured like 2 or 3 years ago now. So, well, we should pump more people into it, yes.
Just another question. You compared your table. One of the columns was Eigen.
Yes.
So how do you compare yourself with Eigen? In terms of obviously
performance.
Linear performance, yes.
Yeah.
Yes. Because here is a list of support, right?
Yes.
And
yes. True,
yeah.
sure.
I mean, you have there some pretty good names, but they kind of compare themselves more or less okay. But Eigen seems to be bar MKL. Eigen seems to be king of the hill, right?
Eigen is actually our damn nemesis somehow. It's actually funny because we win on some point. For example, we have a larger support of ICIDs than Eigen. So if we want to cheat, actually we take a 16 cores machine with AVX2, and we are the king of the hill. The point where Eigen is still better than us, but we are working on it. It's on small-sized matrices. Well, we know what to do for that. I mean, we just didn't bother right now because our first experiment was requiring, 10 of 1,000 stuff.
Eigen beats MKL on
yeah,
sizes.
I know. And they beat LAPACK, and they beat a lot of stuff because, when you have 4 elements in your matrices, well, I can write the LU decomposition myself on a small paper, and it will go faster than the full-blown algorithms. So, but we are trying to fix that. That's the point where they get very better performance than us. For historical reasons, we didn't bother with this kind of small stuff because, well, it's not what we needed to solve at the beginning of the project. We're now looking at that and try to fix this. I think we fixed it, or I have a branch where we fix already for the small matrices on element-wise operations. That was quite trivial to do. So if you do A equal B plus C divided by cosinus of X, and all your matrices is 3 elements, it should be faster than a couple of days before. The other stuff we try to fix is that we found that trivially, quite strangely, that there is none of those libraries actually deals with multi-cores except in big kernels. And what we found out is that, I mean, if you want to start firing Openmp threads, let's get simple. If you have 16 elements, there's no way it will be faster. So I have a student working on a small static cost model. So you look at the IST at compile time, guess estimate, the complexity of the operations, look at the number of elements, and if it's not big enough, okay. Even if I have multi-thread, I will just do the classical stuff and you don't pay for whatever. That's ongoing work, and that's currently the main selling point of Eigen. If you have very small matrix, use Eigen maybe, or use bigger matrix, I don't know. And on the point of linear algebra, so that's the next step. We didn't want it to waste efforts re-implementing the whole damn thing. So we use LAPACK right now and BLAS.
And could BLAS?
And could BLAS whenever, you know.
Okay. Do you have support for that?
Yeah. Yeah. Okay. Well, we have support for that through the Magma binding actually, because Magma requires QBLAS. So whenever we use Magma, bang, you have QBLAS. We still haven't non-Magma related CUDA supports. That's incoming next for different reasons, because again, so what happens if you have too small matrices and so on? So we have to solve these cost model issues, and then we probably be in. The other point is that we didn't want to spend efforts rewriting all those linear algebra algorithms, because the guy from LAPACK knows their stuff inside out, and most of the time that's the best algorithm you have, except for, some critical algorithms that nobody actually knows how to write. What we're trying to do now is actually not requiring LAPACK anymore, because all LAPACK algorithms are basically BLAS function dancing together. So if you have, like we do for LU, we can reconstruct a more parallel aware algorithm, and we just depend on BLAS. And we will probably have a look at writing a boost SIMD implementation of BLAS. And so we can have the choice between using some pre-existing BLAS LAPACK binding or going through our systems. That's, again, an ongoing work, yes. Okay, thank you.